So in the next couple lessons, we're going to review integration with exponential functions and logarithms, and we're also going to, in the next section, go over exponential growth and decay. This chapter is really focused on applications, and I thought it would be a good idea to go over and review exponential functions and logarithms, since we are going to review also exponential growth and decay. But now that we have a little bit more experience under our belt, when I go through these topics, I'm going to go into a little bit more depth with them. So in Calc 1, we went over this rule here, the power rule for integration, where if we have some power function and we integrate, we add 1 to the exponent and then we divide by that n plus 1. And then, of course, we add in our constant. However, this will work for all values of n except for -1, because when n is -1, that's going to force us to divide by 0, and we all know what happens when we divide by 0, the world blows up, so we don't want to do that. So in Calc 1, we talked about the rule that when you take the derivative of the natural log of x, we get 1 over x. And so therefore, working backwards, we would get that the integral of 1 over x dx would be the natural log of x. So this clears up the case of what we need to do when n is -1. However, now I'm going to do a little bit more than just giving you the rule. We're going to actually prove it. And we use implicit differentiation for this. So I want to take the derivative of the natural log of x and show you that it is 1 over x. So I'm going to say let y be the natural log of x, and then using exponential form, we can rewrite this as x is equal to e to the y. Now what I'm going to do is I'm going to use implicit differentiation to take the derivative of this. So I take the derivative of x, which is 1, and then I take the derivative of e to the y, which is e to the y, and then using the chain rule, because we know y itself is a function with respect to x, so we're going to use the chain rule and say times the derivative of dy dx. Now, since we're trying to prove that the derivative of y with respect to x is 1 over x, I'm going to solve for dy dx, and I should get 1 over x. So I'm going to solve for dy dx by dividing both sides by e to the y. So that gives me this, and remember what we said e to the y was when we rewrote this in exponential form. We said that that was x. So when I replace e to the y with x here, I get that the derivative of y with respect to x is 1 over x. So we know now, we just proved it, when y is equal to the natural log of x, then dy dx is 1 over x. Okay, now let's actually practice taking the derivative of log functions. So remember, when you take the derivative of a natural log, it's going to be 1 over x, x being whatever is inside the parentheses. Now, we have to remember to use the chain rule if there's something other than just x inside the parentheses, if there's some kind of inner function. So for this one, the derivative of the natural log of 5x squared minus 2 is going to be 1 over 5x squared minus 2, but we have to remember to use the chain rule and multiply by the derivative of that inner function. And the derivative of 5x squared minus 2 is going to be 10x. And so then when we multiply this together and clean it up a little bit, our derivative is going to be 10x over 5x squared minus 2. Now with this next example here, we have the power rule and the chain rule with the derivative of a log function. When we're using the power rule, remember we bring this power down in front. So this comes down in front. So I have a 2 here, and then this gets decreased by 1. So So I have 2 in front, a 1 as the exponent, and then the inner function stays the same. But because we have an inner function other than x in here, what we want to do is use the chain rule. So we're going to have to actually use the chain rule twice here because this is an inner function, and then we also have 3x as an inner function. So when I multiply it by the derivative of natural log of 3x, that's going to be 1 over 3x, and then multiply by the derivative of 3x, which is 3. And then when we clean it up, we get 2 times the natural log of 3x over x, because I can get rid of these 3's. 3 divided by 3 is 1, and those can just disappear. All right, now working backwards using integration, remember when we have 1 over x, and I integrate, that's going to give me the natural log of x. Here, I'm going to set it up so that I have 1 over some function. So I'm going to let u be x squared plus 4 right here. And then when I take the derivative, I get du is equal to 2x dx. Now, if this is going to be u, I want to end up with 1 over u, so it's in the form where I can integrate as the natural logarithm. So I need to get rid of the x and the dx and rewrite it as something else in terms of u. So I'm going to solve this for x dx, which means I'm going to divide both sides by 2 to isolate the x dx. So I can replace x dx with 1/2 du. So when I rewrite this integral, I get 1/2 du over u, and now it's in the format where I can use the natural logarithm. So I'm going to carry over the 1/2, and then the integral of du over u is the natural log of u, and then of course I want to add in my constant. And then the last step is to go back and resubstitute for u so that you have everything in terms of x. Since the question is asking about integrating with respect to x, we need to make sure that that's how we write our final answer. So when I go back and resubstitute for u, I get 1/2 natural log of x squared plus 4, and then of course our plus constant. Now let's review properties of the natural logarithm, and these properties hold true for any logarithm really. But here are our properties. We have that the natural log of 1 is equal to 0. The natural log of a times b is equal to the natural log of a plus the natural log of b. The same thing goes for division. That would be natural log of a minus the natural log of b. And then we have the power rule where if we take the natural log of a to some power r, we can pull the r down in front and it becomes r times the natural log of a. So the first one's pretty straightforward and easy to prove. We know that e to the 0 is equal to 1. And then if I just write that in logarithmic form rather than exponential form, we get the natural log of 1 is equal to 0. So this one's pretty easy. Now for the last 3, I'm going to use this information right here. I have that I'm going to let x be the natural log of a, y is going to be the natural log of b, and then when we write these in exponential form, we get e to the x is equal to a and e to the y is equal to b. And I'm going to use this for the rest of these 3 proofs here. Now, I'm going to go a little bit out of order. I'm going to prove number 4 first because I want to be able to use this property to prove these 2 here on number 2 and number 3. So I'm going to go a little bit out of order. So I'm going to prove that the natural log of a to the r is equal to the r times the natural log of a, that I can bring this r down in front. So I'm going to start off by using the fact that I have this here, and I'm going to rewrite a as e to the x. So I'm going to replace a here with e to the x. And now I can use the power rule of exponents. When I have a power to a power, then I can multiply. So I'm going to rewrite this as the natural log of e to the power of r times x. So now I'm just going to rewrite ln e to the rx. I'm going to call that m. And I'm going to rewrite this and put it in exponential form. When I put this in exponential form, I get e to the m is equal to e to the rx. Because e to the x, or just exponential functions in general, are one-to-one functions, this tells me if e to the m is equal to e to the rx, then m has to be equal to rx because these functions are one-to-one. So now I have that m is equal to r times x. So now going back to this up here, I have the natural log of a to the r is equal to, we said that we rearranged it and we got it so that this is equal to natural log of e to the rx. We said that this is equal to m. So I'm going to set that equal to m. And we also said that m is equal to r times x. So that's here. And what's x? X we said up here was the natural log of a. So I now have that r times the natural log of a is equivalent to the natural log of a to the r, which tells me if I have an exponent here, I can bring it down in front. Okay, so for the last two, I'm going to use this property that I just proved about bringing the exponents down in front of logarithms to prove 2 and 3. So in property 2, we have that the natural log is a times b, and we let a and b, we rewrote those as e to the x and e to the y. So I'm going to replace a times b as e to the x times e to the y. Now, when we multiply and our bases are the same, I know I can add my exponent. So I'm going to rewrite this as the natural log of e to the x plus y. Using the property that we just proved, I can now bring this x plus y down in front. So I have x plus y times the natural log of e, and we know that the natural log of e is 1. So you can write it in here if you want, x plus y times the natural log of e, but since we know the natural log of e is 1, I didn't bother writing it in. So this right here is equivalent to x plus y, and we said that x was natural log of a and y was natural log of b, so then I replaced with the natural log of a plus the natural log of b. So we just proved that the natural log of a times b is equal to the natural log of a plus the natural log of b. And in the last one, we're going to use that same exact argument, but we're using division, so we're going to subtract our exponents. So everything else is the same, we're just using subtraction now because we've got division with like bases and we subtract the exponents. Okay, so now let's use an example to practice using the properties of logarithms. We are going to condense this and create a single logarithm. And this comes in useful when you are integrating or taking the derivative and you've got several logarithms that can combine into one, which will make integrating or taking the derivative a lot easier. So for this first one, and let me point out that there's different ways to do this. But the way that I chose is I noticed that these all right here had a base of 3, the 9, the 3, and the 1/3. So what I did is I rewrote everything in terms of base 3. So I rewrote the 9 as 3 squared, the 3 just stays as a 3, and then I rewrote 1 over 3 as 3 to the negative 1. And by doing that, what I can then do is use our exponent rule for logarithms, and I can pull any of the exponents down in front. So this 2 comes down in front here. This negative 1 comes down in front here and becomes minus the natural log of 3. And now because everything is in terms of the natural log of 3, I can just add and subtract the coefficients and combine like terms. So I have 2 minus 2 that disappears and I'm left with the negative natural log of 3. So taking a minute to combine things when you can definitely helps out. All right, now looking at the properties of exponential functions, we're going to use that to condense as well for when we take derivatives or when we integrate. And because these are exponential functions, really, these just follow the rules of exponents. So when my base of the exponential function is the same and I'm multiplying two exponential functions, I can add the exponents. Same thing for division, I can subtract. And when I have a power to a power, I can just multiply those exponents together. So using these properties, it makes it easier to simplify first before you take the derivative or before you integrate. So looking at these two examples here, I'm going to simplify this first before I take the derivative. If I took the derivative as is before I simplified, I'd have to use the product rule and the chain rule. And it could get a little bit messy, not too bad, but if I combine them first, it makes it a lot easier. So using the fact that these two bases are the same, I'm going to add my exponent. So I'm going to rewrite this as e to the power of 3t plus t squared. Now I'm going to take the derivative, and I don't have to worry about the product rule. I just rewrite it as e to the power of 3t plus t squared times the derivative of my inner function, which is at 3t plus t squared. This one here, I can directly take the derivative. This one's fairly straightforward. When I take the derivative of e to the 3x squared, I get e to the 3x squared times the derivative of my inner function, which is 3x squared. When I take the derivative of the 3x squared, I get 6x. Let's go through the last few examples of integration and derivatives of exponential functions and log functions. So in this example, I have the integral of 2x e to the negative x squared dx. I want to rewrite this so that I have e to the u because I know how to integrate that. So I'm going to rewrite and let u be equal to negative x squared. So when I take the derivative, I get du is equal to negative 2x dx. So as of up to this point, I have e to the u. What I need to do is still replace the 2x and the dx. So I want to replace 2x dx with something in terms of u. So I'm going to divide both sides by -1 to isolate the 2x dx. So I'm going to replace 2x dx with a negative du. So I have this negative I can pull out in front. The 2x dx gets replaced with the du. And I have e to the u here. That gives me a negative e to the u because I have this negative here, plus my constant. And then because the question asked me to integrate with respect to x, I need to make sure that I finish writing my final answer in terms of x. So then I'm going to go back and resubstitute for u. And I said u is negative x squared. So this will be my final answer. Now, as we scroll down to the bottom of this page of notes, we have integration and derivative rules for log in general, okay, and exponential functions in general. If I have something other than e, if it's a 3 or a 2, it's going to follow this rule here. Same thing here. And then if I have some log function other than the natural log, so if I have a different base other than e, this is going to be the rule that we follow for taking derivatives. Okay, so as we go down here and we practice these rules, for this one here, I can directly take the derivative from this. However, I would have to use the product rule, and I have two different bases for my exponentials. You can totally do that, and you're going to get the same answer. But what I'm going to do is, since I know 4 and 2 can be written as the same base, I'm going to use my properties of exponential functions to rewrite this. I'm going to rewrite 4 to the t as 2 squared to the t. And when I raise a power, I multiply. So 4 to the t can be written as 2 to the power of 2t. And then I have, this can stay the same as 2 to the t squared. And now I can write this as one exponential function with the same base. I have two functions being multiplied together with the same base, so I'm just going to add my exponent. So this is what I get here. Now this is much easier to take the derivative of this instead of having to take the derivative and dealing with the product rule with two different exponential functions. So when I take the derivative of this, if we follow the rule above, we have 2 to the power of whatever it is that you're taking the derivative of, but then you have to take the derivative of your inner function, which is this, using the chain rule. And based on the rule, you also have to multiply by the natural log of whatever base this is here. So if we scroll back up, this is the rule I'm using right here. This gets recopied. You multiply by the natural log of this base, and then if you have to, you use the chain rule. That's what I'm using right here. Okay, now for this one here, this is log base 8, and we have an inner function. I'm taking the derivative of a log other than the natural log, so I'm going to be using this rule right here, where I write it as 1 over whatever this value of x is here, this function, times the natural log of whatever this base is. And then, of course, if you have to, you multiply by the derivative of the inner function if you need to use the chain rule. So that's what we're going to use here. I have 1 over whatever's inside here. That's this here. And then I need to multiply it by the natural log of whatever the base is. That's this here. And that stays in the denominator. Right here, if you can see it. Right here, that all stays in the denominator. And then because we have an inner function other than x, that's 7x squared plus 4, I have to multiply by the derivative of that using the chain rule, and that would be 14x. And then when I clean it up and write everything together, I get 14x over 7x squared plus 4, all times the natural log of 8. Now be careful the way you write this. If you don't put the parentheses around it, the computer is going to think, or your calculator is going to think, that the 4 is being multiplied by the natural log of 8 only. You want to make sure that that whole thing, whatever that inner function is, that whole thing is being multiplied by 8, not just this last item here. Okay, now integration involving exponential functions other than e. Let's go back up and look at that rule again, just as a refresher. If I'm integrating some exponential power other than e, then when I integrate, it's going to be 1 over the natural log of whatever that base is times a to the x plus c. Keeping in mind, we have to remember to use a chain rule if we have to. Okay, so in this example, we have 3 over 2 to the 3x. So what I need to do is I need to rewrite this 3 times 2 to the negative 3x. Now this is something other than x, so we're going to use substitution so we can do chain rule in reverse. So I'm going to let u be equal to negative 3x. So when I take the derivative, I've got negative 3x dx. And because I want to, this is going to be 2 to the power of u, and I want to replace that 3 dx, that's what I want to isolate. So I want to get the 3 dx by itself, which means I'm going to divide both sides by negative 1. And so I'm going to replace 3 dx with negative du. So I have 2 to the u. The negative I can put out in front, and here's my du here. And according to our rule, when I take the integration of an exponential function like this, I do 1 over the natural log of that base times this function here, which is 2 to the u, and then add my constant, of course. And then I have to go back and resubstitute because the question asked what this was in terms of x. So I'm going to go back and resubstitute for u. And I said u is negative 3x. So my final answer for this is going to be negative 1 over the natural log of 2 times 2 to the negative 3x plus our constant.